Hello viewers, in our previous lesson we learnt what is probability and how we can calculate it if we know the sample space or the number of elementary events in it and the number of favorable outcomes or the number of elements in the set defining an event. So, the probability of an event A is given by the number of favorable elementary events upon the total number of equally likely elementary events. For a compound event A or B, if A and B are not mutually exclusive events, then probability of A or B is given by probability of A plus probability of B minus probability of A intersection B. But in case the events A and B are mutually exclusive events, then the set A intersection B will be a null set, which implies the probability of this event, that is A intersection B, will be equal to 0, and hence the probability of mutually exclusive events A or B is given by probability of A plus probability of B. You must have observed that the knowledge of set theory helps us a lot in proper understanding of theory of probability. Try to recall complement of a set and consider this experiment. Here is a container which has 2 pink balls and 3 blue balls. The experiment is to pick up a ball from this container. So, the sample space will contain all the 5 elements as the outcome, that is P1, P2, B1, B2 and B3, that is these are the 2 pink balls and the 3 blue balls. Now, consider event A, that is picking up a pink ball from this container. So, the favorable outcomes will be P1 and P2, and therefore, probability of event A will be equal to 2 upon 5. Let event B is picking up a blue ball from this container. So, the favorable outcomes for this event is B1, B2, B3, and hence probability of event B is given by 3 upon 5. Are these events A and B mutually exclusive? Yes, they are. Also observe that when event A occurs, that is when we pick up a pink ball, then we cannot pick up a blue ball. Similarly, if the ball picked up is a blue one, then it cannot be a pink one. So, at one time at least one of these two events must occur. We define an event not A as an event which occurs when and only when event A does not occur. So, event not A for this experiment will have the outcomes B1, B2 and B3. Similarly, event not B will have the outcomes P1 and P2. You can observe that the event not A is nothing but the event B, and event not B is nothing but the event A. Also, event A and event not A, they are complements to each other. So, we can write event not A also as A complement. By Venn diagram, we can show this as if this is the sample space, and if this is the event A, then event not A is represented by this space which does not contain A. Also, A union complement of A or the event not A gives us the sample space. and therefore probability of A plus probability of event not A is equal to, since probability of A we had 2 upon 5, probability of event not A is 3 upon 5. So, this is equal to 1. Therefore, we have probability of event not A is nothing but equal to 1 minus probability of event A. Thus, we observed that if we know the probability of occurrence of an event, then we can find out the probability of the occurrence of an event not A by subtracting the probability of the event A from 1. Consider another example. Throw a die and observe the number shown on it. Event A, which is defined as getting a number which is less than 3, event B defined as getting a number equal to 3, and event C as getting a number greater than 3. Now, since event A has only 2 favorable outcomes, therefore, probability of event A is nothing but 2 upon 6, since this experiment, that is throwing a die, has 6 elements in its sample space. Similarly, probability of event B will be 1 upon 6, and probability of event C is equal to 3 upon 6. Now, taken in pairs, that is, if we take A and B events, they will be mutually exclusive. Similarly, we can take events B and C, they will be mutually exclusive. Also, event E union event B union event C is nothing but equal to the set containing the elements 1, 2 union the set containing the element 3 union the set containing the element 4, 5 and 6, which is nothing but the set which has all the 6 elements 1, 2, 3, 4, 5 and 6, that is the sample space. Events which satisfy this condition are called mutually exclusive and exhaustive events. And for mutually exclusive and exhaustive events, we have probability of event A or event B or event C equal to probability of event A plus probability of event B plus probability of event C, that is equal to 2 upon 6 plus 1 upon 6 plus 3 upon 6. This is equal to 6 upon 6, which is equal to 1. So, we found that if events are mutually exclusive and exhaustive, then the probability of that event comes out to be equal to 1. Now, consider the next experiment. A card is drawn from a pack of ordinary cards. As we know, there are 52 cards in an ordinary pack of cards having identical shape and design, but they have different names. There are 13 hearts, 13 diamonds, 13 clubs and 13 spades. Consider event E1. It is defined as the card is a heart, event E2 as the card is a diamond, event E3 as the card is a club and event E4 as the card is a spade. If we take event E1 and E2 in pair, then are they mutually exclusive? Similarly, if we take event E2, E3 or E3, E4, we find that these events taken in pairs are mutually exclusive. Also, event E1 union event E2 union event E3 union event E4 gives us the sample space S, because E1 has 13 elementary events, E2 also has 13 elementary events, E3 also has 13 elementary events, and E4 has 13 elementary events. So, that makes 52 outcomes, that is the sample space. Now, since E1, E2, E3 and E4 are mutually exclusive and exhaustive events because their union gives us the sample space, therefore, probability of E1 or E2 or E3 or E4 will be equal to probability of event E1 plus probability of event E2 plus probability of event E3 plus probability of event E4. We know that probability of event E1 is 13 upon 52, E2 is again 13 upon 52, same for E3 and for E4. This is 1 upon 4 plus 1 upon 4 plus 1 upon 4 plus 1 upon 4, this is equal to 1. In general, if E1, E2, E3, En are a set of mutually exclusive and exhaustive events, then we have E1 union E2 union E3 union En is equal to the sample space and probability of E1 plus probability of E2 plus probability of E3, probability of En is equal to 1. Thus, we observe that the knowledge of a system of mutually exclusive and exhaustive events together with the knowledge of non-occurrence of an event helps us a lot in finding the probability theory. Now, let us try to take up a few examples and illustrate the use of this property. A problem is, a coin is tossed 3 times, find the probability of getting at least one head. When a coin is tossed 3 times, then we may get 3 heads, 2 heads, 1 head or no head, that is all tails. So, the sample space will have 8 elements HHH, HHT, HTH, THH, HTT, THT, TTH and TTT. Now, consider event 1 E1 as getting exactly 3 heads, event E2 as getting exactly 2 heads, event E3 as getting exactly 1 head and event E4 as getting no head or all tails. Now, we have to find out the probability of getting at least 1 head. Now, this event will occur if we get 1 head or 2 head or 3 head. That means, event E will occur if E1 or E2 or E3 occurs. That means, event E can be written as E1 union E2 union E3, such that probability of event E means probability of event E1 or event E2 or event E3. But we know that event E1, E2, E3 and E4, they are mutually exclusive and exhaustive events. So, E1 union E2 union E3 union E4 gives us the sample space S, and probability of event E1 plus probability of E2 plus probability of E3 plus probability of E4 will be equal to 1. That means probability of E1 plus probability of E2 plus probability of E3 will be equal to 1 minus probability of event E4, and therefore E1, E2, E3, E4 being mutually exclusive and exhaustive events, probability of E, as we have already said, it is equal to probability of E1 or E2 or E3. So, this is equal to probability of E1 plus probability of E2 plus probability of E3, which is equal to 1 minus probability of E4, as we just now did in the previous page. This is equal to 1 minus, we know that probability of E4, that is getting no head, is 1 upon 8. So, 1 minus 1 upon 8, this is equal to 7 upon 8. Let us consider one more example. 3 dice are thrown and all possible outcomes are assumed to be equally likely. If the sum of the numbers is observed, what is the probability that the sum is at least 16? Second part is the sum is at most 15. We know that in a die the numbers 1, 2, 3, 4, 6, 5 and 6 are marked on the 6 faces of it. So, when we throw a die, then there are 6 possible outcomes. So, the sample space has 6 elementary events. Similarly, if we throw 2 dice, then the sample space will have 6 into 6, that is equal to 36 elementary events. Similarly, if we throw 3 dice, then the sample space will have 6 into 6 into 6, that is equal to 216 elementary events of the type 111, 112 and so on, 666, 665. So, the sample space for this experiment has 216 elementary events. Now, consider the first event, that is getting the sum at least 16. But before we do that, let us first see if we throw 3 dice, then what possible sum do we get? The minimum sum which we can get is 1 plus 1 plus 1, that is equal to 3. We may also get 1 plus 2 plus 1 or 1 plus 3 plus 2 and so on. The maximum sum which we can get if we throw 3 dice is 6 plus 6 plus 6, that is equal to 18. Now, let us come back to the event, that is getting the sum at least 16. This event will occur if the sum is 16 or the sum is 17 or the sum is 18. Let us define the first as event A, this one, that is sum is 17, as event B, and the third, that is sum is 18, as event C. The favorable outcomes for the first event, that is event A, it will be 664, 646, 466, 655, 556 and 565. That means that there will be 6 favorable outcomes for event A, and therefore, probability of event A is equal to 6 upon 216. Now, for the event B, that is getting a sum equal to 17, these are the favorable outcomes for this event, and therefore, probability of B will be equal to 3 upon 216, because this event B has 3 favorable outcomes. Similarly, event C has only 1 favorable outcome, therefore, probability of event C is 1 upon 216. But are these events mutually exclusive? Yes, they are, and therefore, for mutually exclusive events, we have already said that probability of event A or event B or event C is given by probability of event A plus probability of event B plus probability of event C. This is equal to 6 upon 216 plus 3 upon 216 plus 1 upon 216, which is equal to 5 upon 108. Therefore, probability of the sum at least 16, we got it as 5 upon 108. Now, consider the next event, that is getting the sum at most 15. Now, this event will occur if the sum is 3 or 4 or 5 and so on, but it cannot be 16 or 17 or 18. That means this event, that is getting the sum at most 15, is a complementary event to the event sum at least 16. So, instead of finding all the 13 probabilities for this event and adding them up, we can say that probability of event sum at most 15 as 1 minus probability of event, that is sum at least 16, because they are complement to each other. This is equal to 1 minus, since we already know the probability of this event, so we substitute this value 5 upon 108, and this is equal to 103 upon 108. Thus, we observe that if E1, E2, E3, En are a system of mutually exclusive and exhaustive events, then E1 union E2 union E3 union En is equal to the sample space, and probability of E1 plus probability of E2 plus probability of E3 so on plus probability of En is equal to 1. This implies probability of E1 plus probability of E2 plus probability of E3 plus probability of E of n minus 1 will be equal to 1 minus probability of En, because this probability is 1 less than this probability of En, or probability of E1 plus probability of E2 plus probability of E3 so on plus probability of En minus 2 will be equal to 1 minus probability of En minus 1 plus probability of En. Now, we take up a few more examples to clear this idea of a system of mutually exclusive and exhaustive events. A couple, husband and wife, appear for an interview. If E is the event, husband is selected, and F is the event, wife is selected, what is the probability for the husband or the wife to be selected? Now, consider the event E1 as only husband is selected, event E2 as only wife is selected, event E3 is both are selected, and event E4 as none of them are selected. So, event E1 says only husband is selected, that means only husband and not wife. So, we can represent it as E and not F. In Venn diagram, we can show it like this. If this set represents event E and this is F, then we just shade the portion which represents E and not F, and therefore, event E1 is nothing but the set E intersection complement of the set F. Now for the event E2, it says only wife is selected, that means F and not E, not the husband, only wife. In Venn diagram, for this we shade the portion which represents only F and not E, and therefore E2 is the set F intersection complement of the event E. Now E3 event says both husband and wife are selected, that means E and F. So for this we shade this portion in the Venn diagram, and E3 represents the set E intersection F. Lastly, event E4 says neither husband nor wife is selected, that means not E and not F. In Venn diagram, we can represent this set by shading the portion outside E and F. That means E4 represents the set E complement intersection F complement, which is equal to E union F complement, where the set E union F represents at least one of the two events must occur. Also observe that the events E1, E2, E3 and E4, they are mutually exclusive. If this set is E1, that is only husband, this is E2, that means only wife, this is E3, that means both husband and wife, and this is E4, that means none of them are selected. So we find that E1, E2, E3 and E4 are mutually exclusive and exhaustive events. Therefore, E intersection F complement union, E complement intersection F union, E intersection F union, E complement intersection F complement will give us the sample space S. Also, probability of E intersection F complement plus probability of E complement intersection F plus probability of E intersection F plus probability of E complement intersection F complement will be equal to 1. This implies that probability of E intersection F complement plus probability of E complement intersection F plus probability of E intersection F will be equal to 1 minus probability of E complement intersection F complement. But we know that probability of E intersection F complement plus probability of E complement intersection F plus probability of E intersection F is nothing but probability of E union F, and therefore probability of E union F is given by 1 minus probability of E complement intersection F complement. Thank you.